Alright guys, so in this video we'll continue our series on complex analysis, and we have the trigonometric study to be there. Then we have example 1 to be 1 plus I equals 2. We take the modulus of 1 plus I, that's the square root of 2. Then we multiply it with 1 over, we multiply it with the initial problem, that's 1 over root 2 plus I over root 2. Then we take inverse cos of 1 over root 2 to be cos pi over 4, and inverse sine of 1 over root 2 to be pi over 4. So we have the properties there as well. So take look at them. Then we move to the argument of a product of complex numbers for a non-zero complex number z and z prime for any integer n. If we are asked to look for argument z times z prime, it is argument of z plus argument of z prime times 2 pi. Note that the 2 pi can also be separated, that is plus 2 pi k, where k is a real number. K can be 1 or 2. Argument of 1 over z is minus argument of z 2 pi, which is also congruent to minus argument of z plus 2 pi k. So we have an example there. We have it to be z equals to minus root 3 plus I 1 plus I squared. So we take the argument separately. Then from the Morvis theorem, we know that the power of 1 plus I raised to power 2, we bring down the 2 after taking the inverse tan of 1 over 3. That's, of course, that's the argument. So we have it to be 5 pi over 6. So we have the second argument. Then we apply z1 over z2 to have our final answer. So we have some other properties of complex analysis. We have 1 over z. The modulus is 1 over the modulus of z raised to power n. We have it to be the z raised to power n. Then from the Morvis theorem, we are asked to solve 1 over root 2 plus I over root 2 raised to power 1999. So from this case, we have our r to be 1, that is our modulus to be 1. So we take the inverse tan of 1. Inverse tan of, when you take 1 over root 2, that's inverse tan of y over x, will give us 1, which is still the same thing as pi over 4. But from the Morvis theorem, we multiply the power with the pi over 4, and we represent 1999 as 2000 pi minus pi over 4, such that the minus pi over 4 is representing our principal argument, plus 2 pi times 250, where 250 can represent k. Our k is 250. That was an error. K is equals to 250. So we have our final answer to be that. Then we move to the exponential denotion of a complex number. So we have our definition to be there. Now the exponential part is also confused to be the trigonometric part. Cos e raised to power I alpha is cos alpha plus I sine alpha. Note that 1, what should we do to have 1? 1 is still the same thing as cos 0, but sine 0 is 0. So it means that 1 can be represented as cos 0 plus I sine 0, which is still the same thing as e raised to power I 0. Then we have minus 1. Minus 1 is cos 180, that's cos pi. Cos pi is 1 minus 180 plus I sine pi. Then we have it to be e raised to power I pi. Now this brings out our Euler formula. So we have it to be e raised to power I pi plus 1 equals to 0. That's our Euler formula. Then we have some example to convert from the algebraic form to the polar form. So the formula is r e raised to power I theta. But note that r, which represents the modulus, is square root of 2 e raised to power I. When you take the inverse tan of 1, you have it to be 45 degrees, which is still the same thing as pi over 4. Then we have the second example, 1 minus I to be e raised to power square root of 2 e raised to power minus I pi over 4. We also have some other examples there. 1 plus I square root of 3. We have our answer as stated. Then we have the properties. We have the properties z and z prime be two non-zero complex number. So z times z prime will give us r times r prime e raised to power I open bracket alpha plus alpha prime, same as 1 over z is 1 over r e raised to power minus I alpha. Then for z raised to power n, that's r raised to power n e raised to power I n alpha. For z over z prime, that's r over r prime e raised to power I alpha minus alpha prime. So we have some examples there as well. So let z and z prime be two complex numbers such that z equals to 3e I pi over 4 and 1 over 2 e raised to power minus I pi over 4. So we are asked to evaluate z times z prime. So it means that we're multiplying the two non-zero complex number. So we have our final answer to be 3 over 2 for the first part, e raised to power I pi over 12. The second part, z raised to power 5. Z itself is 3e raised to power I pi over 4. That's 3 raised to power 5 e raised to power I times 5 pi over 4. So the last one, we have 1 over z, and we already know the value of what z is representing. But coming back to the previous example of -1, which is cos pi plus I sine pi over 4. So what you do is you manipulate things out and check which one will give you 0, if cos pi will give you 0 or sine pi will give you 0. So that is why you must have at least, must give you 1. I mean, it's either cos pi will give you -1 or I sine pi will give you -1, but one of them should give you -1 or the other one should give you 0. So that's how we arrive at e raised to power I pi. So we have some other properties. The properties of the let alpha be a real number such that e raised to power I alpha equals to cos alpha plus I sine alpha. So we have to prove from the Euler formula that cos alpha is equals to e I alpha plus e minus alpha over 2. Similarly for sine alpha, but sine alpha is having over 2i. So we have e raised to power I alpha already given. Then if we multiply through by a negative sign, we have it to be cos alpha plus I sine alpha. Then on subtracting the two of them, we have it to be equals to 2i sine I alpha. Then make sine alpha the subject of the formula. We have our answer to be there. So similarly for cos alpha as well, we have it to be e raised to power I alpha plus e raised to power minus I alpha over 2. So that is that for this video. So you check the tutorial questions and solve everything for better understanding on complex analysis. Thank you.